My name is Anna. I'm a developer at a consultancy called Carbon 5. We build digital products. We work with all kinds of clients, everything from startup through enterprise. We have offices all over the US. Like a lot of people here are hiring, so if you're interested, talk to me afterwards. In the vein of this talk, I co-founded an organization called Elixir Bridge. We help underrepresented folks in tech learn Elixir and Phoenix. So we host free workshops on the weekends at various companies around the Bay Area. We've had them in other parts of the US. We get companies to sponsor food and space. The goal is to kind of help grow the community. Also, shameless plug, for those of you interested in the Elixir community, I started a podcast with a couple of folks. It's available on iTunes and Spotify. It's called Elixir Outlaws. If you're interested in any other conversation we're having, check it out. So what do I want to talk about today? Kind of what is, hopefully people can see my slides, but what is Bitcoin and the blockchain? How does it work, and why might you try and build it in Elixir? So in the vein of a lot of the work I do teaching folks and bringing them into the community, if you're new to Elixir or new to cryptocurrency, that the goal is hopefully you can walk away with a better understanding of both of those things. So if we talk about, and the cryptocurrency that we are going to see an example of or try and implement today, we're kind of using Bitcoin as an example. They're not all the same, but we're modeling after the Bitcoin protocol. So if we talk about the question, what is Bitcoin? There are lots of definitions, but some people might say uses the blockchain to implement a decentralized ledger for payments. Others might say secure, depending on who you talk to, anonymous store of value. But I want to take a step back before we get into all of that and talk for a minute about what we think value is, right? And in something that we actually understand. So value in the context of money today. And if we think about the definition of money, something we're all very familiar with, we use it to pay for goods and services. We can use it to pay off debts, to maybe pay taxes. But what really determines its value? And if we look at our history, it wasn't until that recently that money was backed by precious metals, right? The first bank in Europe, I actually think, was started in Stockholm. I think I have that right. And the banknotes, was it? Oh, I thought somebody said something else. The banknotes that were written or given by that bank were backed by gold and silver. Fast forward, we're all familiar with the gold standard. In 1940s, 1944, a bunch of countries got together. We've heard of maybe the Bretton Woods Agreement, and they said we're pegging our currencies to gold. So why, right? Why were precious metals valuable? Any thoughts? Yes. Any other thoughts? So there's scarcity, there's durability. They were arbitrarily divisible, right? And they were durable. But fast forward again, at least in the States, 1971, Nixon was worried about inflation. He said, we're not doing that anymore. We're not pegging our currency to precious metals. It's going to be a fiat currency. But the dollar still had value. So why? Well, similar reasons, right? The Federal Reserve controlled the flow of money, so there was a level of scarcity. You could still exchange it for goods and services. You could pay taxes. But the last point is a little bit more nuanced, that people were betting on the future of the US economy, that it was going to do well, so the dollar would keep its value. So if we go back to Bitcoin, the real big idea about cryptocurrency is that we can do digital value transfer over the internet, right? We have something of value that's completely digital, that's not backed by other collateral. And the same principles apply, right? At least for Bitcoin, there's a level of scarcity, because eventually the number of coins will be finite. You can exchange it for goods and services. You can't maybe pay your taxes in it yet, but people are betting on the future. And there's also this element of anonymity and security, right, that I mentioned. So before we get further into that, I just want to take a step back and talk about a little bit about cryptography and that history. Especially in the States, cryptography was really an admission of the government and the military until the late 90s. And in the 70s, with the advent of computers and the change of how information was shared, cryptographers, especially early cryptographers at that time, were worried about how individuals were able to keep their privacy, right? They wanted to use cryptography to kind of break the monopoly of the state. Some of you may be familiar with this photo, but later in the 90s, there was an organization that was formed called the Cypherpunks, and by Eric Hughes, John Gilmore, and Timothy May. And the whole idea behind this organization is they really believed in an individual's right to privacy, and that just because you wanted privacy and anonymity did not mean that you had something to hide. So in 1995, Eric Hughes, they had a large mailing list, lots of subscribers. He released what was called the Cyberpunk Manifesto, and it talked about how privacy is really necessary in the digital age. Banks and governments are not going to do this for you. And that cypherpunks not only needed to talk about it, but actually build the tools to do it. And so many of the cypherpunks actually made early attempts at digital currencies that failed. One of them that's many people know about, it's called Hashcash. It was created by Adam Back. And while the currency didn't succeed, there was a concept from it called proof of work that we use in Bitcoin and we'll talk about in a little bit. So 2008 happens. Everything crashes, right? And this conversation that's been happening in the cypherpunk community is revitalized. The idea that we want an alternative place to store value that's outside of the government. And in 2009, Satoshi Nakamoto releases Bitcoin. So whether or not it's coincidental that Satoshi was part of the cypherpunks or just took inspiration from them. And by the way, for those of you who aren't familiar, we actually don't know who Satoshi Nakamoto is, the entity that released Bitcoin. But Satoshi would describe it really as a secure way to transfer money or value over the internet digitally without the need for a middleman. Okay, so we got to this point. How does it actually work? Well, we talk about it being decentralized, right? We can just think about it as a bunch of computers or nodes all over the world. And each one has the exact same copy of what is essentially a list, right, that eventually achieves consensus. And these nodes communicate via something called the gossip protocol. And I thought this was an interesting analogy for how the gossip protocol spreads information, right, similar to social network or how epidemics spread. But really, the idea is that a node will send a message to its peers, which will send a message to its peers, which will send a message to its peers. So before we go any further forward, I want to take a moment to talk about asymmetric cryptography, because that's what's used to make sure that transactions and things on the network are secure. So on the blockchain, if you're participating in the network, you will have a public and private key. So let's say I wanted to send Bob a Bitcoin. I would sign that with my private key and send along my public key. And when Bob receives it, he can decrypt the message and validate the transaction, knowing that it came from me and nobody tampered with it. And another important thing to note is that there's no concept of accounts on the Bitcoin network, right? You go on to Coinbase or something, you buy several $100s worth of Bitcoin, but there's nowhere that says you have an account with this much money, really. All it is there's a transaction, remember, it's just a ledger that gets written to the ledger saying this transaction happened and you have this much money. So now let's say I want to take half of that, I want to take one of those Bitcoin, let's say I bought 2, and send that to a friend of mine. So I create a new transaction that takes this old one as input, and I send one of them to my new friend Bob and send one back to myself. And so the old transaction is no longer valid. And this new transaction, we call them unspent transaction outputs. So how do these transactions actually get added to the blockchain? So when a transaction gets sent on the network, actually these transactions get captured in a pool, and when a miner or a node is adding a block to the blockchain, again, we are eliminating some of the complexity, but they'll essentially choose which transactions they want to add. And then they will hash them by 2s up a tree until they get a root hash, right? Also called a Merkle root, and this structure being called a Merkle tree. And among other reasons, but one of the reasons that they do this is that we all know that when we're hashing things, if we change the input to the hash, the output becomes much different. And so, again, it prevents anybody from tampering with the transactions, and the nodes can actually communicate amongst themselves and help each other validate if they have a question about any portion of their tree. Okay, so we added transactions to a block, but how do we add a block to the blockchain? So this is where this concept from Hashcash proof of work comes in, right? These nodes are all distributed, and they all have a copy of the blockchain. And Satoshi was thinking that the way the network works is that everyone is always building off of the longest chain. But if it's really easy to add blocks, then it's really hard to achieve consensus on who is actually leading the blockchain. So they thought that every node would have to do a little bit of work. And once you solve a puzzle, and then once you solve a puzzle, you can add the block. And so how does this work? So the blockchain network actually has what's called a work factor. There's a level of difficulty for this puzzle. Essentially, do a computation where the output is a hash with a certain number of leading zeros. And the content you use to get that hash, and again, we're eliminating some of the content, but really it's a hash from the previous block, the root hash from your Merkle tree, a timestamp, and a nonce. A nonce being an arbitrary value that gets incremented until you actually mine the block, solve the puzzle. And then once you do, you can send it off to the network saying, hey, I'm adding this block, I solved this puzzle. And if you're the first one, and it's valid, it gets added to the blockchain. So really, what this did is it allowed the nodes to agree on how the ledger would be updated. And it solved the problem of who was able to influence consensus. This isn't really the case anymore because you have caching power that's very concentrated. But when this was released, the idea was that if hashing power was equivalent, right, across machines or across nodes, and everybody had equal probability of mining a block and the equal ability to achieve consensus. And this idea, right, of working off of the longest block, this idea of consensus is called Nakamoto consensus. So we talked about how it uses blockchain to implement a decentralized ledger for payments. Nodes send messages using the gossip protocol. So we need a system that's decentralized, that is concurrent, and communicates via message passing. So as I started digging into these topics and as I was teaching, I was like, oh, this would be a really interesting example to implement in Elixir given the nature of the language. And so we are going to implement, this is kind of an example. This has been running for a while because I wanted to show you an example. We have 3 processes that are each running and communicating with each other. And we'll talk about this, but they're each mining a block, adding it to their blockchain, communicating the blockchain out, and then if the blockchain that they receive is new, they will update their chain. So if we start building, we'll start with transactions. And again, just a qualifier, I would not run this code in production. This is a demo. There are definitely things you would think about with regards to security and complexity, but bear with me. So let's take a look at our transaction module. We'll break it up and take a closer look. And for the purposes of this, we are only mining 1 transaction per block for simplicity. But really, we have a transaction module. We are going to have a struct that is going to have an address to which the blockchain is going from, our public key. And then we're going to sign the transaction with our private key. And sign will look like that. And we'll also be able to validate other transactions that come in, checking their public key. So we know we need to somehow build a chain of blocks. So we're going to start with a single one. So we're going to have another module. Sorry, that's kind of small, but we have another module. It's going to have a struct, but it's going to have a nonce, which is that arbitrary value that we increment, the hash from the previous block, and a transaction. And then we are going to essentially do that computation, right? So a closer look at that create function. And eventually we're going to mine the block, and then return the struct. And really, all this function is doing is what we talked about. It's hashing and iterating over and over and over again. Did anybody see Sonny Scroggins' talk on NIFs yesterday or in San Francisco? So I don't think he did the demo maybe yesterday, but he actually, something that would be interesting here, because this is very computationally intensive, and something that I was in the process of doing but didn't finish in time for showing it here, is actually offloading some of the computation into Rust using NIFs, and then sending that information back to the Erlang process to actually make it faster, especially when the work factor gets really high. Okay, so we have a block. How do we create a blockchain? So we're going to create another module. It has a few module attributes. Take a closer look. We're setting the work factor low, just for the purposes of the demo, to make it quick. The name of our module and a block reward. And I didn't mention this earlier, but block miners actually get a reward for adding blocks to the blockchain. I think right now it is 12.5 Bitcoin per block. It halves every so often. I looked it up earlier. I think it's going to halve again in 2020. So in a few years, the reward will be half of what it is today. And eventually, there'll be no more reward, right? So it'll be interesting to see what happens with the value of Bitcoin when that happens. And so we're going to have initial state. Again, you wouldn't store this in memory, but we're going to for the purposes of this demo. We're going to have a struct with some blocks and our private key and our public key. And again, for those of you who are newer to Elixir, we're going to use an agent to store this in memory. It's really just an abstraction around background processes that store state. And it'll take an initial function that it will implement as our state. And again, because we want to make sure that this process is running, and if it dies, you want to spin it back up again, we are going to leverage, right, OTP. We're going to use a supervisor, which is really just a specialized process that monitors other processes. So in our application module, we're going to bring in the app supervisor behavior bringing in use supervisor, and then really we call startLink on it, and we pass it a list of arguments. The name of our module, initial arguments, a strategy. There are several of them. We're just saying if our process dies in this case, spin it back up again, and the name. And then in our blockchain module for our supervisor, we need to define a child spec so that when our supervisor is starting our module, it knows exactly what it's doing or how to start it, right? We give an ID, we tell it what function to call on start. Our child process will be a worker. It will always try to restart, and how long to wait before shutting it down. And so we know that supervisors allow us to make fault tolerance easy, and that's kind of what we want. So if we look at our blockchain module again, we're going to add a block. We're going to check if the transaction is valid. If it is valid, we're going to mine that block and add it to our blockchain. Agents make that really easy because we're just going to call update and give it our new blockchain. And update the head of the list with our new block. Okay, so we have transactions, we have a block, we have a blockchain. How are we actually going to communicate between other nodes? So again, leveraging another behavior from OTP, GenServer, which allows us to implement client-server interaction really easily via a series of callbacks. To set up a GenServer, we're just going to bring in use GenServer. Again, startLink, we'll pass it our module name, and startLink takes init as a callback. So we're going to give it a map with our ID, an empty list for our blocks, and UUIDs. So in this example, we're sending a unique ID with each message so that if a node has already received that message, it doesn't have to process it again. It can just skip it. So it keeps track of all the messages it's received from other nodes before it processes them. And because the gossip protocol is fire and forget, it is asynchronous requests. We can make asynchronous requests using GenServer by calling cast function. And again, I mentioned it's a series of callbacks. So handle cast. We'll make a request here saying we're going to mine a block and gossip it to our peers. Handle cast is a respective callback for that, right? So essentially, we're going to mine a block, update our state, send it out. And the GenServer does maintain state. So it'll return it at the end of every callback. Okay, so we updated our current state, but we might want to see it, right? So GenServer allows us to do that by making a synchronous request via genserver.call. Again, it'll match, the callback will match against the arguments that are passed in. So the respective callback handle call will match against that and return our state. Okay, so what happens when we actually send it out? How are other nodes able to receive it? Well, we make another asynchronous request, right, with different arguments. But in this case, right, we send a request to our module name and also the peer, right? Not just the name of the module. So if we give it the peer address and then give it the full IP, there's no difference between sending it to a process on my machine or another node somewhere else, right, on the network or somewhere else in the world. And so you can see how initially it would be easy to implement something like this protocol using Elixir. So then the callback for that, right, is handle cast. It'll match against the arguments. It is going to check that it hasn't processed it, and then it'll check that the blockchain is valid. And how does it do that? Well, remember that each block has a hash that's pointing to the previous block, right? So if I have the second to last block and the last block, once I solve the puzzle, this is the hash that this block is going to use to point to it. So it's really easy to go back once we have all those values and actually make sure that all of those hashes are valid and roll through each block in the chain. So then if the blockchain is valid, it'll say OK and start building off of that chain. And here we kind of want to mimic the idea that a block is mined on the on the Bitcoin network roughly every 10 minutes. That's kind of what affects the difficulty of the work factor. It goes up and down to make sure that that's happening. We're going to kind of mimic that and say we want to mine a block every 30 seconds. And GenServer allows us to have a callback that will handle requests that aren't specified, right? If we're not specifying the type of request. So in this case, we're saying schedule a message every 30 seconds. The handle info callback will match against that. Send our message, schedule it again. And again, we want to keep an eye on this process because it's what's communicating between our other processes. So we just add another supervisor to our supervisor list. And again, because it's a gen server, it has a default child spec. We don't need to define that. And how do we actually connect these nodes, right? So if a process is the ones that are running on my machine, and just give them a short name. And then we can use node.connect to connect to our peers. And if we connect nodes 1 to nodes 2 and nodes 1 to nodes 3, nodes 2 and 3 will be connected. I was going to actually try and do this across on a friend's machine and connect across machines. The network here wasn't really happy and didn't want to allow me to do that. But again, you wouldn't do this in real life because this probably isn't secure. You can give it a full name with a full IP and a cookie, right? And the cookie is used for low-level authentication because this is all happening via TCP IP protocol. Again, don't do this in production. You'd probably want to run it over TLS. Make sure it's secure. But yeah, for those of you who walked in and didn't see, this is running. If we were to look at the blockchains at various points, like if we were to pull these up, and I realize it's a little hard to do as I was showing this demo, you can see the blockchain swap for the latest chain. And that's all I have. Any questions?